Well, welcome back, everyone. Looks like we can get started with our week number 12 we're on. After the end of week 12, we're 75% through with the entire semester, but this is the part of the semester that seems to go the fastest. So welcome back, everyone. We're just about to start chapter 20, looking into the difference between two proportions. We'll start with a confidence interval problem and then end with a hypothesis test. But the bigger announcement is that our exam 3 has now been written. This one is underway. It's going to be a shorter exam compared to what we did on exam 1, exam 2. This one is just going to have 3 questions. All of them are going to be a complete analysis of, in chapter 18, this one is either going to be a confidence interval procedure or a hypothesis test, looking at the difference of two population means, mu1 and mu2. Then chapter 19, this will be the second question on exam 3. This one is going to deal with just the single proportion, and that's what assignment number 9 is based off of. This one will either be a confidence interval or a hypothesis test. And if we go a hypothesis test on mu1, mu2, this one will be a confidence interval, and vice versa, just for extra variety there. Then chapter 20 is going to feel pretty similar to what we did in chapter 18. We're going to look into the difference of two proportions. But for a hint on exam 3, this one will specifically be a definite confidence interval procedure, because that's the first one we're going to do in chapter 20, and that will give us the most time to prepare for that last chapter on the third exam. So that's the plan so far. This will be our last in-class exam. And as a reminder, the final exam, in lieu of doing a big project, the final exam is just going to be a take-home exam that we're releasing on the day before finals week. But any questions or comments at the moment, folks, with the exam 3 or any other announcements? Okay, well, the way exam 3 has been supported is exactly the same way as exams 1 and 2. There'll be a formula sheet. That formula sheet is going to help out with whichever procedures might come up on these 3 questions here across the chapters. As well as extra practice, you can take a look at the sample exam 3 exercises version 1. These are the ordinary lecture notes we've been going through, converted into essentially worksheets, really. And version 2 is more stuff, but these are brand new problems that we haven't assigned or done in class. So they're great. This is a great version to take a look at just for a fresh take on new problems. So this will be our third exam. It feels like it's coming up pretty fast after our exam 2, which was before spring break. But again, once we get through this one, we're just home free on the course. Well, any last questions at all, folks, before we take a look at what's going on in chapter 20? Okay, well, let's open this up and get started. Chapter 20 just kind of leads off what we did in chapter 19. We're dealing with categorical data with 2 outcomes, except if there's 2 proportions, really what's happening in this chapter is there are, in fact, 2 categorical variables. And this is the table that we've been building out since we got to, say, chapter 19. It's starting to grow quite a bit. If we have 1 quantitative variable, we use the chapter 17 methods. If there's 1 quantitative variable along with a categorical variable with 2 outcomes, that means we're looking into the difference of population means. And that's what puts us into chapter 18, the first question on exam 3. If there's exactly 1 categorical variable with only 2 outcomes denoted success failures, then that's the chapter 19 problems that we finished off, assignment number 9 essentially. And now here's where we are currently. We have two categorical variables on the table this time. Both variables have exactly two outcomes. The first variable we're going to think of as successes and failures, but the second variable is just telling us which population we're considering in the first place. Much like the categorical variable when we're looking into one quantitative data, looking into the difference of means. So if we have exactly two variables with exactly two outcomes, we're doing a chapter 20 method, and we'll continue extending on these analyses to see what happens if, say, we have one quantitative variable and a categorical variable with, say, 3 outcomes or 4 outcomes, and so on. So that's where we're at so far in the analysis. And here's how the methods start off. It should look like deja vu. We've cited this theorem before. This is how we went from one mean into two population means in chapter 18. And we're just going to reuse it again. This is going to tell us how to go from one proportion in chapter 19 into two proportions in our chapter 20. So here's our nice theorem that says we can combine means. If we're adding or subtracting variables, the means of those variables add up. We can combine variances in a similar way. Whether you're adding or subtracting the variables, variances will only add. And the standard deviation would just be taking a square root of the variable. But our variables say x in this problem and y are going to be substituted with p hat 1 and p hat 2. So that's the idea with this problem here. And let me match up my color coding just a little bit better. I guess x is blue, y is green, so let's keep that going. So p hat 1 and p hat 2. So this is how we're going to work the theorem. It starts off with the typical context of any problem in chapter 20. We have two independent simple random samples. One categorical variable is going to tell us what population we came from. The sample sizes will be N1 and N2. And these are from populations that have true population proportion of successes, P1 and P2. So those are the parameters in the problem. And the central limit theorem that we looked into in chapter 19, is just cited twice, one for each statistic, p hat 1, and again for the next statistic, p hat 2. So p hat 1 is distributed in this way. The center, or we could call it the mean, the center of that normal distribution is p1, and the standard deviation is this entire square root. And then, let me fix my color coding. That was supposed to be in blue. Color coding seems a little tricky this Monday. Then for our next population, that's true population proportion P2 of successes, that's a parameter. But the statistic, the actual thing we calculate from the data, is p hat 2. Its sampling distribution, like we looked into chapter 19, is normally distributed approximately with center P2, the parameter, and that's the standard deviation. Square root of P2 times 1 minus P2, divide by sample size 2. So essentially, this is the essential limit theorem written down twice. Only thing that changed is which population, 1 or 2, are we talking about? Well, any questions at all, folks, with the setup before we look into the sampling distribution of the difference, p hat 1 minus p hat 2? Okay, well, to get the sampling difference of the sampling distribution of the difference in sample proportion successes, we have to know what its center is, the mean. That's what this theorem above part 1 is providing. So we can start by saying, with that in mind, the mean of p hat 1 minus p hat 2, that's the difference in sample proportion of successes, is P1 minus P2. So all we've done here is we've taken this mean and this mean, P1, P2. If we're combining the parameters, p hat 1 minus p hat 2, Then we just subtract those two means. So that's going to be the center, the first thing that goes in our specification for the normal distribution of p hat 1 minus p hat 2. Now, if we can get this part where the red dot is, the standard deviation, our work is done. It's trickier. It's kind of what we had to do in chapter 18. We have to start with the variance and then work from there. So if we square these portions, the standard deviations, we'll get the variances. So let's work this out in stages. We can say the variance of p hat 1 is raise that entire thing to power 2. But when you square that, it just peels off the entire square root symbol. And so you get p1 times 1 minus p1 divide by sample size 1, n1. And likewise, same exact thing for the second statistic, p hat 2. And the variance for p hat 2 is squaring this, peels off the square root, so we just get p2 times 1 minus p2 divided by sample size n2. So we haven't used the variance formula here yet from the probability theorem, but now we can. We know exactly what the variance is, written in blue, written in green. We're doing a p hat 1 minus a p hat 2, but just because we're minusing doesn't change that plus there. That's a solid plus. Variation only increases when we combine these kinds of random variables. So we have the mean. On the next level, we can say the variance of p hat 1 minus p hat 2, the difference in sample proportion of successes, is from this red dot here, we take the variance from the first one, and we found it to be this. So take that, p1 times 1 minus p1 divided by sample size n1. Add to it, the plus there came from that part of the theorem. Then grab the second variance. That one is right here. So we take plus p2, 1 minus p2, divide by sample size n2. A lot of symbols to write down. The variance starts to get pretty complicated, but at its essence, this is the exact same steps we took when we were in chapter 18. So just for the sake of comparing the methods, chapter 18, we found out what the mean was because we just pulled it from the normal distribution, the central limit theorem for means. From both these portions here, the mean of the difference of x bar 1 minus x bar 2 was just the mean, mu1 minus mu2. Here, it's a different statistic. This is a sample proportion of successes, p hat 1 instead of x bar 1, and same for p hat 2. But we're not doing anything entirely different. We just go to our new central limit theorem, grab the first element here, that's the center, or we call it the mean, and subtract them. Next thing we did is we had to get the variance, which meant we squared that portion where the red dot is. Squaring this gave us sigma 1 squared divided by n1. So there it is. Likewise, we got the same quantity here. Then when we looked into the variance of the difference, we just added them together. Here, that's the same analogous thing. It's just a lot more messy. When we add the variance for the difference of these two statistics, that's what we get next. And the very next thing we do is, to get the standard deviation, you square root whatever you got in that step. So we're going to take the square root, throw it all together into a new central limit theorem, not for the difference of means, but for the difference of population proportions. So that's the logic of what we're going to do in the next steps. Any questions or comments at the moment? Okay, it's a lot of writing, but we're just about there. Let's put down the next level and say the standard deviation of p hat 1 minus p hat 2 is the square root of, and it's always kind of amazing how big you have to make that square root symbol, let's just the square root of the variance. So it'll go P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 divided by sample size 2, N2. Once we have that, we can state our central limit theorem. And here it is. The central limit theorem for a difference in sample proportions. When we say that central limit theorem, all we're really saying is what the approximate sampling distribution will be for the difference in those sample proportion successes, p hat 1 minus p hat 2 once again. So here's how it goes. We take p hat 1 minus p hat 2 is distributed approximately normally. So we'll have to have some good information when we do a confidence interval or hypothesis test to tell us when that's a good approximation. But what we put in next is just the mean, P1 minus P2. So go P1 minus P2. Then for the next part, we put in that standard deviation that we derived, and it's P1 times 1 minus P1 divided by N1 plus, same exact structure, just update the subscript to A2. P2 times 1 minus P2 divided by sample size 2. So that's our entire brand new central limit theorem. Once you get a central limit theorem, you're basically one stop away from getting the entire confidence interval formula. And just for the sake of parallelism, to see what we did in the past, once we had this, we mentioned we have approximations. Both portions here, the first portion and the second portion, are unknown. But in chapter 18, when we wanted a confidence interval, we had to estimate this right here. We used the statistics. S1, the sample standard deviation, estimated sigma 1, the population standard deviation. Then all we did was put S1 here, S1 there, squared them as appropriately. And that's where this standard error came from. Here we're doing the same exact thing. P hat 1 right here is an estimate for the unknown P1, which is also this entire portion here. Likewise, P hat 2 is an estimate for this portion right here. So even though both parts are unknown, we can give a really good estimate for this part right here. So let's write out that step. The standard error for P hat 1 minus P hat 2 is going to be equal to the square root of, first we put in the estimate just using P hat 1. We throw it in right here. Take P hat 1 times 1 minus P hat 1, divide by sample size N1, and then just do it all over again. This stuff is unknown, but we've got a ready to go estimate. That's P hat 2. So in place of the unknowns P2 and 1 minus P2, we put in P hat 2, 1 minus P hat 2, divide by N2. So we have it. If the sample sizes N1 and N2 were the same, we could simplify this a little bit and add across the numerators, but we're leaving it in this form because in practice, they can be different values. So we allow for procedures where the sample sizes, although not ideal, we can still analyze data with unbalanced sample sizes where N1 and N2 are unequal. But now that we've got the standard error, we can give the full confidence interval for P hat 1 minus P hat 2. Much like over here, once we got the standard error, we want the confidence interval for X bar 1 minus X bar 2. This is all we did. We put in the difference. This estimates the difference mu1 minus mu2. We added or subtracted a critical number T star because that was a two-family distribution, both mu and sigma. And then we just multiplied it by the standard error we derived. We're doing almost exactly the same thing, except one bonus here is we used Z star once again. And this is P hat 1 minus P hat 2. So that's where we're at on the next level. We're about ready to state the entire confidence interval procedure, and then we'll look into how the problem goes for doing an estimate. Any last thoughts at all, folks, on this derivation to get to that spot here? Okay, well, confidence intervals are pretty straightforward. The hypothesis tests, they're different. In chapter 19, there were different things we had to do. In chapter 20, hypothesis tests are even weirder. We're going to come back here when we look into how the hypothesis test goes, what the new statistic is going to be, what the new standard error comes out as, because of what happens when you assume the null hypothesis is true. So hypothesis testing always has a little bit more going on. That's why we start with confidence intervals. It's like a warm-up before getting to those steps there. So here is our full procedure all laid out. A lot of this probably looks pretty familiar, but let's pay close attention to where the changes are. We're going to use this procedure to estimate the difference in population proportions, P1 minus P2. Here, we have to make sure that we have now two simple random samples from two independent populations with the unknown proportions, P1 and P2. Here, we're not meant to do a careful reading of the study, actually buying the study, reading everything we know about it. So here we'll just briefly discuss. Based off whichever information the problem gives us in its short write-up. After that, we have to recall everything here is based off a central limit theorem, which gives us an approximate normal distribution. We want that approximation to be effective, and that means sample sizes have to be large enough so that there's enough successes and enough failures in the sample. So here's where we're going to do a more careful check, but also notice these numbers are different. We have to have the number of successes and failures in the sample, so not expected successes, failures, when we do a hypothesis test. They have to exceed 10. So this is the expected, the number of successes in sample 1, number of failures in sample 2, likewise, number of successes in sample 2, number of failures in sample 2. If one of those inequality fails, then our method is not going to be reliable. We can still do the confidence interval, but when we say with 95% confidence, that part may not be accurate. The confidence might be way lower, or the normal distribution could be so off that's just no longer appropriate to use these procedures whatsoever. So here we will carefully check. And give counts, much like we did in chapter 19, of successes, failures, but now it's two samples, so we have to do this for both samples. So when you do this, say, as a homework question or in a question on, say, exam 3, let me walk that back a little bit. On the third exam, just like we did on exam 2, I focused more on the method and the practical conclusion, less on the condition checking, just like exam 2. So mainly for the homework, when you're doing these as a homework, make sure you show the number of successes and failures so that I know that you know exactly what they are, and then we double check against this criteria. The last part, we'll briefly discuss once again that the two populations have to be large or the normal distribution fails in a different kind of way. The normal distribution is really approximating something different, a kind of binomial distribution. And that approximation goes badly. We start to lose independence if our sample is too large. So as a rule of thumb, although we want large samples, so part 2 holds, it can't be too large relative to the population, or the procedure breaks down in a different way. And our rule of thumb, just like in chapter 19, is each population should be at least 10 times larger than its respective sample. This is not something we can carefully check unless we do research, honest research on the demographics of the problem or the biology of the problem. So here we'll also just briefly discuss what we know based off the brief context. So just briefly discuss. So that's the condition checking side. We'll take a look into that on the very next problem, how each part goes. Any questions at the moment before we go to the actual mathematical side, the interval itself? Okay, well, here's the whole interval. To provide a level C percent, say 95% to 99% and so on, confidence interval for the difference in the unknown parameters, P1 minus P2, we calculate the statistics, subtract them, then add or subtract another critical number Z star, just like in chapter 19, multiplied against the standard error that we derived, and that's the whole entire confidence interval. So this right here is the estimate for the unknown difference, P1 minus P2. This is the standard error. That's its exact formula there that we derived. And once again, Z star, you could just go to chapter 19 or even chapter 14 all the way back there to do a table lookup. But it doesn't hurt to just pre-compute it fresh in each problem. If you don't mind, you could just say Z star is Q norm, 1 minus the confidence level, divide by 2, set lower dot tail, equals false. And either do a table lookup or just compute it fresh. Either way, Z star is usually a fast part of this procedure. Well, now that we have all that under our belt, we're ready to do a statistical analysis. And this one addresses a pretty upfront question. It says right out of the gate, is cocaine deadlier than heroin? I mean, they're both deadly, and that depends on the context, absolutely, which one is going to be worse. And so we have a specific context. So this is a real study reported in the Journal of the American Medical Association, and it found that rats, these are laboratory rats, with unlimited access to cocaine, had poor health, had more behavioral disturbances, and died at a higher rate than did a corresponding group of rats given unlimited access to heroin. So again, that's our specific context. If I had to guess which is more deadly, I probably would have said heroin. But in this context of unlimited access in a cage where the rats are placed, looks like cocaine was worse. But we're going to go beyond that. We're going to not just say cocaine was the more deadly drug for these rats. We're going to say by how much more deadly was it? And that's what the confidence interval is going to provide. So here's how this study was done. In this experiment, it was an experimental design. 200 rats were randomly assigned to the two treatment groups indicated in the table below. So here's the table. So 100 rats then were given unlimited access to cocaine. 100 rats were given unlimited access to heroin. And this is the percent dead after 30 days. The one thing I should mention here, because the context isn't too clear about it, is when they say it was an experimental design and the 200 rats were randomly assigned to two treatment groups, they didn't say how many rats went into each group. But if they had 200 rats, the more natural thing that they would have done is split them up, randomly assign 100 to go into the cocaine group, the other 100 to go into the heroin group. So let's make that our assumption here. Sample size 1 is going to be 100 rats. Sample size 2, N2, will be 100 rats as well. So cocaine here, we can think of as p hat 1. P hat 1 is going to be the number of successes. Well, this is about the data is given in terms of dying after unlimited access for 30 days. So the success here, even though it's kind of sad, is that the rat has died to the experimental condition it was subjected to. So p hat 1 is going to be x1, the number of successes, divided by n1, which would be 90 divided by 100. That's why we have 90% dead. So the value here would just be 0.90, going from the percentage to the decimal. So this is for the cocaine group. Then likewise for the heroin group, the heroin treatment, Our next statistic, the one we call p hat 2, will be the number of successes x2 in the second treatment over the sample size n2. There were 36 successes rather, out of a sample size of 100, so we get 0.36 altogether. So that's our context. It says for us to provide a complete analysis of the data using 99% confidence in this question. Well, all we're really going to do is run through these methods, check out the conditions, and pretty much proceed just like we've done before in the prior chapters. Just a new context of this time two population parameters we're estimating, P1 minus P2. Any questions before we get fully started on the procedure? Okay, well, this one is a complete analysis. On the exam, I have it broken down for all three questions more as a part A, part B, part C, and so on. Homework questions tend to go like this a little bit more often, so we'll follow this format. We want to state the practical question, indicate that requires statistical inference. I mean, that seems to be the practical question, the first sentence written down in the problem. So if you cited that, that would be completely fine. And we've done that a number of times just to convey it's okay to just cite the problem itself. But this time, let's go a little bit different. Let's put this in our own words and say, in the context of unlimited access for 30 days, is cocaine or heroin more deadly to, these are lab rats, I'll say either just rats or lab rats. I'll go with just briefly rats, deadly to rats by considering you could say the percent dead or the proportion dead. After 30 days, but we've already said 30 days, so that'd be redundant. And that seems to be the practical question that also pulls into the context. If we were thinking about, say, ordinary people, and they're in a similar context, it might be somewhat similar, but it's very specific with unlimited access in a time frame of 30 days. Well, now that we have that down, the next thing we want to say is, what is P1 minus P2, this thing at the very top? We have to really nail that down because our job is to estimate it with this procedure. And if we're not too sure what we're estimating, the whole conclusion step becomes very, very vague. So let's say once and for all what P1 is, what P2 is. The statement part right there kind of gets us started because our subconscious is thinking about the context as we write out this parameter. We'll say here, we're calling one subscript, the cocaine group. So let's keep that order the same all the way through the question. Let P1 and P2 denote the proportion, not of the 200 rats in the experiment or the 100 per each one of the groups, but we want to think of all lab rats being subjected to the same exact experimental condition. So we'll say it this way: proportion of all rats that will die after being given unlimited access to, that again, let's keep the correspondence the same, cocaine and heroin, respectively, for 30 days. So those are our two unknown parameters. When we said the words respectively, we meant that P1 corresponds to cocaine and P2 corresponds to heroin. So we've got our parameters down. Next thing we need to look into is to see, are the conditions even met for these data? Then we'll run through the mathematics of the confidence interval itself, this part up here. Well, any questions at all, folks? Writing down the parameters? Okay, well, as far as condition checking goes, the first thing we'll take a look into is, do we have random data? Well, we have 200 lab rats, but this was an experimental design. So this was kind of an extra special study in that certain sense. These rats are bred and treated in a way that they're all very, very similar. They're probably all about the same age, probably about the same weight, health conditions, and so on. We want them to be all very, very similar because once we randomly assign them to the two different experimental conditions, we want to say that the change in survival rate here was caused by these experimental conditions. So the fact that this is an experimental design means the conclusions can now be about cause and effect in this problem here. But it also means when we took these 200 rats and randomly assigned them to two experimental conditions, that qualifies as obtaining a simple random sample. So we can say automatically on part one, since the rats were randomly assigned, you could say to the two different experimental conditions, I'll say more briefly to the two treatments receiving either cocaine or heroin, randomly assigned to the two treatments, we have two simple random samples, and at the same exact time, those samples are independent. We're really looking at two different populations at this point, a population of rats exposed to cocaine versus heroin. So let's say here, we have two simple random samples. Let's say it differently. We have two independent, simple, random samples. So as long as they really randomized and assigned these 200 rats to the two conditions appropriately, the randomization is an absolute pass on this one. And when we say we have two independent simple random samples, that's what this choosing a method portion was all about. We have two categorical variables with two outcomes. The one categorical variable is success failure. Success being that they died because we're studying that outcome, failure meaning they survived. But the other categorical variable, also with exactly two outcomes, is what population do they belong to, the cocaine or the heroin? Which parameter are we talking about? So that's what the second categorical variable is controlling, the fact that there are two independent populations, and it just tells us which rat or which population each of the 200 rats really belong to. So we pass on that side. But now the next thing we have to take a look into is 200 rats a large enough sample size for the central limit theorem to be effective? And that's going to fully depend on the number of successes and the number of failures we have in the sample data. So that's our next stop. We have to look into both populations. So let's start with the cocaine rats. I'll just say briefly, cocaine group. In the cocaine group, a success is the outcome of dying. 90% dead, but out of a sample size of 100 means 90 successes altogether. So we have 90, which is greater than or equal to 10 successes. And that's the benchmark we have to hit. It has to be at least 10, so greater than or equal to 10. There was 90 successes, but the sample size is 100. That means there was only 10 failures. 10, which just barely hits that boundary. This is very borderline data, actually, even though the sample size was all the way up at 200. 10 greater than or equal to 10 is true. We barely make it. If that was 91 rats that died, only 9 successes in the sample, and the sample size of 200 would not have been large enough. But we're okay so far. So we hit these 2 requirements for the cocaine group. We do it again for the heroin group. We're looking for at least 10 successes and failures in the sample. Looks like we'll be okay since this one is closer to the middle of 50. So for the heroin group, there was 36, which is greater than or equal to 10 successes. There's 36 successes, and in a sample size of 100, that means altogether there'll be 64, which is greater than or equal to 10 failures. So once again, those 2 benchmarks are met. We're at greater than or equal to 10 on both of sides here. So that means the total sample size of 200 was large enough. The sample size let's say it this way, the sample sizes of first one was 100 in the first group, and N2 was 100 for the second group, are large enough. So that's great. We can now analyze these data with a little bit more confidence. Again, it's borderline, but the rule of thumb that our author gives us of greater than or equal to 10 is conservative in the sense that our method is still going to be quite accurate, even if we hit the borderline value right there on the number of failures. Last thing we have to double check is the entire method collapses if our sample size is too large. The population should be at least 10 times greater than the sample size. But if we're talking about industry standard lab rats, there are a lot of these, hundreds of thousands, I would guess. These are bred continuously to help experiments go around the US, around the planet. And so the fact that we had sample size of 100 here, 100 here, that absolutely was not too large. That's pretty small against the population sizes of all lab rats. So we can say here just briefly, since lab rats were used, the populations are much larger than 10 times the sample sizes. Okay, well, this looks like a pretty bona fide set of data that meets all of the requirements for our conditions. All we're going to do now is run through the entire set of motions for obtaining the confidence interval itself. We'll use the data here. I'll use it in this form that shows the values for p hat 1, p hat 2, and the sample sizes n1, n2. First thing we're going to want to do is come up with the standard error, get the critical number z star, and then we'll be on our way with the next steps. Let me shrink this down just a touch. Well, any last questions at all, folks, before we go to finish off this problem? Okay, let's first, just for the sake of kind of getting it in our head, let's just write down the method. The method will be to take p hat 1 minus p hat 2. We've already got those values down below, so that's ready to go. Add or subtract a critical number, z star. So we'll double check our confidence level and just pre-compute it from scratch. And really the big step of this whole process is we also need to calculate the standard error of p hat 1 minus p hat 2. So let's take our time doing this computation right here. By formula, standard error of p hat 1 minus p hat 2 is going to be the square root of p hat 1 times 1 minus p hat 1 divided by sample size n1. Then do it again, p hat 2 times 1 minus p hat 2 divided by sample size n2. So this is going to be the square root of. And we have our p hat 1, p hat 2 down below here on the screenshot we put in. So dropping in the 0.90, first over here, we get 0.90 times 1 minus 0.90 is going to be 0.10. Sample size N1, well, it was 100 for both groups, but we can also read it off here from the denominators. Since we didn't reduce a fraction or do anything like that along those lines. Then do it again for p hat 2, take the 0.36, plug it into these spots. So 0.36 times 1 minus 0.36 is 0.64. And then divide by 100 again. So this is at the stage we just reach for a calculator. We'll take the square root of 0.90 times 0.10, divide by 100, add to that this part, 0.36 times 0.64, divide by 100, and that's our standard error. I'll go to about 6 decimal places on this, 0.056604. And let me double check my digits. 0.056604. Okay, I think we've got it. Next big thing we need is Z star, but again, that one is not too bad. That's a quick computation. Z star is going to be Q norm 1 minus, but we should double check the confidence level just so we don't get the wrong value there. Confidence level is 99%, so we're going for a high level of confidence. And again, this is the syntax we're using here, cited in the notes in purple. So reusing that syntax, let's go 1 minus 0.99, divide by 2, lower dot tail, equals false. And nothing happened. Hang on. That's weird. Let me try again. Something's weird with my RStudio session. Q norm 1 minus 0.99 divided by 2, lower dot tail equals false. Maybe I put in the parentheses weirdly or something along those lines. Okay, we got it this time, so we're all set. I'll go with the 2.575829. So Z star 2.57, and I already forgot the digits. Let me try again. 5829. Remembering sets of digits is not my strong suit, but we get through it together. After we have these two components here, we can now just put this all together. Let me move this down just a little bit further. So we have so far, in place of p hat 1 minus p hat 2, we can put in 0.90 minus 0.36. That's a percent dead for the cocaine group, percent dead for the heroin group that we cited down below here. Add or subtract our critical number Z star, that's the 2.575829. Multiply against standard error, 0.05. 6604. Okay, we're nearly there. We just need to run that through the calculator. So let's start computing these lower bounds and upper bounds next. So I'll park this over here. For lower bound, go 0.90 minus 0.36 minus 2.575829 times 0.056604. Definitely double check the digits, make sure everything's in there right. Here's our lower bound. I'll round this to 4 decimal places at this point. 0.3942 is less than, and in the middle, we're not putting p hat 1 minus p hat 2. We're putting in the difference of population parameters, p1 minus p2. Then go back here, redo it all over again with the plus. And one small helpful thing here is the parentheses algebraically are superfluous. You could drop them. But it helps remind you that the plus thing, the thing you're changing from negative to plus is not here, it's out here. So it's more mainly just for the sake of extra insurance. So I don't flip the wrong sign. That's a common mistake on this one. So flip that to positive. Our upper bound is 0.6858. And now we have the difference of survival rates or death rates, is the way it's actually phrased. The difference in death rates between the cocaine group here, P1, and the heroin group here, P2. And we can go even one step further just to make our interpretation flow a little bit better with the actual English we put down on paper. Let's solve for P1 in the middle, just like we did in chapter 18. And you'll get P2 plus 0.3942 is less than P1, which is less than P2, plus 0.6858. Finally, that's our entire interval. Both sides are positive, so that's going to tell us about our practical conclusion. But just like we did on exam 2 and emphasize on our homework assignments, when we give a practical interpretation, whether it's a confidence interval like this one or hypothesis test, the main thing we're interpreting first before we make any additional statement is a direct interpretation of the interval we produced, or the alternative hypothesis that we either accepted or failed to support. So to give that direct interpretation, we go all the way back to the top, recite how we define the parameters, and just read them out one last time with this interval in mind, and the fact that this was 99% confidence. Well, any last questions or thoughts, folks, before we give the final touch on this one? Okay, let's write this out. First thing to remember is the confidence level. So let's say that part. With 99% confidence, now the next thing we're focusing on is this entire statement right here. We're just reading it out left to right as we see it. Well, not exactly left to right. We're working from the middle and outside as we see it, but we're using our words, saying what the context is. So what we did in part A, just like you'll see on the exam, this will be the part A answer. We just cite that as we read out the interval. So let me focus on the part in the middle. That's the P1, which is the true proportion of all rats being given unlimited access to cocaine specifically. So we need to say the proportion of deaths. We have to mention what the success is in this as well for all rats given unlimited access to cocaine. So I read out the P1 part. Now we're going to say is from 0.3942 larger up to 0.6858 larger than the value for P2. Same rats, but unlimited access to heroin. So we'll say is from 0.3942 larger because we see the plus. If it was a minus, we'd say smaller than, to as much as this much larger, to 0.6858 larger than, we have to say larger than what, but now we're focusing on the P2 portion, and that's just the same rats being given unlimited access to heroin. So we don't have to say, well, let's read it out, say this way, then these rats, let's maybe use all, just to emphasize the population, then all rats given unlimited access to heroin And let's put in that important part of the context for 30 days. So we've got all the elements. We mentioned the first parameter, P1, unlimited access to cocaine. Second parameter, P2, same thing, unlimited access to heroin. We have to say what the proportion is for in the first place. What was the success? We mentioned it here when we said the death. We say at what the interval goes from this value to this value. If it was a minus to a plus, we'd say from that much lower to that much higher, but it was larger on both ends. So what that tells us is, yeah, cocaine was much more deadlier. They were about 40% almost more deadly to almost 70% more deadly than it was for those rats given heroin. So if we want, we can make that one additional statement. In this context, cocaine was more deadly for these rats. But when it says give a practical interpretation using the context, this is the main thing that we had to say first. Let's in fact just let our problem land on this as our ultimate conclusion. It does address that cocaine is more deadly, so it does answer the practical question that we laid out on the first step, which is more deadly, cocaine or heroin? But we not only know which one's more deadly, we know by how much. The margin of error is huge, by as much as almost 40% to almost 70%, using those specific proportions. Well, that's the adventure for two population proportions. The work we do on this one is really very similar to what we did in chapter 19 with one proportion. And also this follows the same exact kind of logic we did in chapter 18, two population means. In fact, if you took a look at some of our methods in chapter 18, say this one, we're looking into totaling versus control dopamine concentration in a certain region of the brain. We eventually got a confidence interval, which looked like this, pretty similar to our confidence interval on the left. Once we got the values, we had a difference of parameter in the middle of that confidence interval, just like what we had here, almost exact same correspondence. And then we solved for one parameter in terms of the other, just so that our conclusion at the very end would flow a little nicely. So there's some really, really strong parallelism between what you do in chapter 18 versus what you do in chapter 20. Well, any last questions or thoughts, folks, about either one of these methods? Okay, and just to go back to the Canvas page here for one more moment, what we just completed here is essentially the last question that will occur on exam 3. Exam 3, it does use your work in chapter 20, but it's only going to be a confidence interval problem. So you'll just get a new context. It's going to be a part A, B, C, D, and so on, rather than state, plan, solve, conclude. But you're really going to do the same kind of steps that we did here, minus the condition checking. I think the condition checking we'll usually say for the homework and the final exam in order to not make the exams too large. Well, with what we're going to do next, we're going to get started to see what it's going to look like when we do hypothesis testing. And to get into hypothesis testing, we have to be really careful with how this goes and cite the central limit theorem again. So we'll come back to this when we're back in class on Wednesday, but here's how the start of all this goes. Suppose we are doing not just a confidence interval, but a test of hypotheses at the same time. That means if we're in chapter 20 doing all this, we have two independent simple random samples from two populations which have these unknown population proportion successes, parameters P1 and P2. So there's the parameters in the problem. We're going to test these hypotheses, which are, once again, let's cite chapter 18, very similar to the hypotheses we tested in chapter 18. Where are those hypotheses? I went too far. Let me scroll back up to the top here. There they are, finally. So we have this null hypothesis in chapter 18 that mu1 minus mu2 is 0. Likewise, the null hypothesis in chapter 20, we're only looking into one specific null hypothesis, that the parameters P1 is equal to P2. So the null hypothesis is a statement of no change in the population. But for these kind of contexts, whether it's mu or p, quantitative versus categorical, what we're saying is the populations are the same, that the population means are identical, or here, the population proportions are identical. Then we have other alternative hypotheses, either a not equals, a less than, or a greater than. But no matter what the alternative hypothesis is, the first step we take, no matter what, in order to come up with a p-value is we assume H naught is true. And it's a massive assumption. It was a big deal in chapter 19. And it's an even bigger deal here. If you assume the null hypothesis is true, you assume that P1 really is exactly equal to P2, no difference in the population. So let's make that statement here. This means P1, in fact, equals P2. I will give it a new symbol. It's some common value we'll call P naught. 0 here to mention from the null hypothesis. So if that's true, the sampling distribution of p hat 1 minus p hat 2 changes by a lot. So let's write this out. First, let's just cite it here just for easy reference. P hat 1 minus p hat 2 is distributed normally with center P1 minus P2 and standard deviation. Let me change this to make sure I can fit this in. P hat 1, or excuse me, that's the standard error, just P, no hats. P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. So that's the central limit theorem for the difference in population proportions. But if the null hypothesis is actually true, you have a value now you can put in. You can put P naught right here because P1, P2, it's the same exact parameter. So we can now say P hat 1 minus P hat 2 is distributed normally. And in this position, that's just going to be a 0. That's P naught minus P naught. So just a 0 right here. P1 minus P2, well, if they're equal, it would come out as 0 altogether. You know, it doesn't hurt to make that a little bit more clear. P1 minus P2 through this assumption is P naught minus P naught, but that's just a 0 now. So we have a 0 right there in the null hypothesis. And likewise, a big change right here. The numerator is completely the same now. In the numerator, we have that P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. Well, both P1 and P2, those population parameters, they're a common value P naught now. So this becomes P naught times 1 minus P naught over N1 plus P naught times 1 minus P naught over N2. That means you could just factor out the entire numerator, P naught times 1 minus P naught, from this entire side right here. This is what it would look like. P naught times 1 minus P naught. When you factor that out, it just leaves behind the denominators. 1 over N1 plus 1 over N2. So in this step here, we factored out P naught times 1 minus P naught. So our central limit theorem, which had one particular format here we derived on the top of the notes, changes radically. Now it's this. On every single hypothesis test you do in chapter 20, because your first step in getting a p-value assumes the null hypothesis is true, this is now your central limit theorem. It takes on this form. Let me box it out just so that the comments in orange are less of a distraction. So we now have that new sampling distribution for the difference in the statistic. And that means our standard error is going to change as well in a pretty big way. But any questions at the moment, folks, with this structure here? Okay, our next thing to get is that standard error. But notice one thing that's still kind of a tragedy about this. We have a value 0 here, and 0 is absolutely known. It's right there on paper. But just because we assumed P1 equals P2 equals P naught, doesn't mean we know what that value is. P naught is still unknown. So this is our first struggle in getting the standard error. P naught is unknown. But we've got to estimate it. Every time we came up with a standard error, we went to the spread here, the standard deviation and the normal distribution, and estimated the parameter that came out. This time we have to estimate P naught. We've never done that before, and it means we need a new statistic. The estimator for P naught is called P hat. That's kind of a concern because this is not the chapter 19 P hat. Not chapter 19 P hat, and that deserves an exclamation mark. This is a pooled sample proportion successes. What it does is it takes your number of successes in sample 1 from population 1, number of successes in sample 2 from population 2, pools the sample sizes, sample size 1 plus sample size 2, N1 plus N2, coming from these sample sizes above, and that's our new statistic. This is the pooled sample proportion of successes. And it's a weird statistic coming out of nowhere. The reason this is the right statistic, however, is we're assuming that null hypothesis is true as our very first step in this hypothesis test. That means the populations are the same. And if the populations are the same, the parameters are equal to each other. Both of the statistics, P hat 1, P hat 2, are estimating the same exact thing. So if we pull successes from both samples into just one statistic, P hat, it's an estimator for P naught. So now we can say on the next level, then P naught is approximately equal to this brand new statistic P hat, and the standard error for P hat 1 minus P hat 2 is going to equal this. That's what we wanted to come out with the standard error, not the same standard error whatsoever for what we just did in the confidence intervals, because we have a whole new sampling distribution. This standard error becomes square root of P naught times 1 minus P naught times, or hang on, I'm just citing this. Let me backtrack. In place of those P naughts, forgot that critical step, we use the statistic. P hat times 1 minus P hat times 1 over N1 plus 1 over N2. So the statistic gets just dropped right here. And that standard error is just coming from this structure right here. We just make the estimate that P naught is approximately equal to P hat and write it in that way. So once we have that all together, we'll now have the test statistic for testing these hypotheses. But it's quite an adventure to get to this brand new standard error. Again, we have to be really careful. If you're doing a confidence interval, like you would be doing, say, on exam 3, your standard error is just this, quite a bit different. The statistics are different. That's P hat 1, P hat 2. But if you do a hypothesis test, like say on the next assignment, number 10, you have to know in that hypothesis test, you calculate this new P hat and a brand new standard error. It all feels kind of random unless you track exactly what's going on with all these steps in example 3. That's part of the challenge in chapters 19 and 20. Our formulas look really vague and almost random how they come together, but it's all tracked through what was the central limit theorem, and what does assuming the null hypothesis is true, what does that actually do in our problem? How does it really impact the sampling distribution? Well, any last thoughts or comments, folks, before we go to the test statistic next? Okay, well, finally, here's our test statistic. Let's cite our hypotheses just to have them in mind as we write this out. We're testing these hypotheses here, and the statistic that's going to do that test for us, leading to a p-value, is going to be this. It's a z-test statistic because this is based on the normal distribution. We take p hat 1 minus p hat 2, not the same as this p hat. So these are the ordinary sample proportion of successes. And already that deserves a big warning all in its own. P hat and p hat 1, p hat 2 are different statistics. So we go back to the ordinary sample proportion of successes, p hat 1 minus p hat 2. We divide it by the standard error of p hat 1 minus p hat 2, which is from this formula right here. Now, all this measures is the number of approximate standard deviations that the statistics are away from each other when you assumed the populations are exactly the same, that those statistics should have been close. If you assume the populations are the same, P1 equals P2, but we find that when we look at one population or one sample and the other sample independently, and they're pretty far away, that would tell us that the null hypothesis is probably false, and that the reality of the problem is that the parameters are actually different. So let's write down just one more comment here, that this is equal to the approximate number of standard deviations that p hat 1 and p hat 2 are away from each other when they should have been close, when h naught, p1 equals p2, is assumed true. So if that comes out as, say, 3 standard deviations, the test statistic z is something like 3.2. We have a lot of numerical evidence against the null hypothesis, evidence in favor of the alternative. We're calling it approximate standard deviations because that's the exact standard deviation all the way up here in part B. But because we divide by the standard error, that's all the standard error is trying to do, approximate the standard deviation in the problem. So we've got the full method. If you can get the test statistic to match your null alternative hypotheses, then we can get a p-value. So really the big thing that's hard about this problem, hypothesis testing, is what the standard error actually looks like. It's a pretty random looking formula, and you have to recall you're using a different statistic, this new p hat here. Well, we did it, folks. That's our full derivation of the hypothesis test. When we come back on Wednesday's class, we'll run through, as a refresher, the pooled sample proportion, our weird standard error that we derived, look into this summary information of the p-values, and do a hypothesis test here before we move into chi-squared procedures. Well, we're definitely not going to try to rush through that in less than a minute and some change. So any last thoughts or comments at all, folks, before we call it a day? Okay, well, have a great afternoon, folks. On Wednesday's class, we'll refresh on how this procedure goes and move on over to this new problem. Once again, our exam 3 is going to be just these 3 problems here. And the problem we just concluded on, problem number 20, will be the last question that can occur on exam 3. So if you have any questions about the upcoming exam, when we come back Wednesday, we'll start by taking questions and then just continuing through the chapter 20, potentially looking into the chi-squared procedure right after. But have a great afternoon, folks. I'll see you all Wednesday.